And hello, welcome back OpenFoamers, YouTubers, welcome back. We are going to look at the JouleHeatingSolid case. So in the last video we talked about this multi-region heater with some radiation properties. So today we want to look at Joule heating. Alright, so anyway, the address is here in the OpenFoam. So I'm going to copy and paste to the GitHub directory. So GitHub software. And let's go to OpenFoam heat transfer, and I'm going to put in the chtMultiRegionSimpleFoam, CPAR, this whole thing, JouleHeatingSolid, and I want to put it here. Okay, so that's done. I want to remove the copy multi-region heater because we don't really need that anymore. That was just like a reference case for us to, play around with the code and see what's going on. So we can take a look at the JouleHeatingSolid this time. Okay, I'm gonna quit this thing. Okay, so let's go to, maybe we can copy the JouleHeatingSolid and then we can play around with it. Copy JouleHeatingSolid. So we have another file we can like play around with. We can go to the copy and then okay, now we are set up to experiment. So let's take a look again at what we usually do. We want to look at the all run file. So all run file, it's just all run pre and then it runs the application chtMultiRegionSimpleFoam. So nothing too much there. Now the challenging part, of course, is the all run pre, because it takes a pretty long while to set up the case. However, in this region, we only make one region, right? So run application solid block mesh, and then the region is solid. Okay, so we can take a look. Oops. Can take a look at the constant, and then we see only one region. So this is the simplest thing we can do for chtMultiRegionSimpleFoam. Alright, QA, okay, clear, and then we can do the G, which is the gravitational acceleration, and we can take a look in solid. And we can take a look at thermophysical properties. Alright, so thermophysical properties, we have all of this. Thermotype, He solid thermal, pure mixture, blah blah blah. And this looks like a molecular weight of 12. In the transport, we have a kappa of so much. Okay, thermodynamics, we have fusion, latent heat of fusion, and this heat capacity. And this equation of state, which just determines its density, and it's kind of fixed. Does look a lot like graphite to me, as in the molecular weight is 12. I could be wrong, maybe it's something else, but that is my guess. I don't know why the roll is so heavy for graphite, but that's another topic for another day. Okay, so this is a very straightforward kind of a case. You can even see the parallel as well. So it does all run pre, and then it runs the decompose parallel for the region, the solid region, and then reconstructs it, the parallel dictionary to like the latest time, and then it's just the same thing as before. Nothing too fancy. So let's take a look at the other things. Oopsie, CD system. So via control dictionary, so chtMultiRegionSimpleFoam, blah blah blah. So we do have a sample, sample 1. So it's under the type sets. Library is in library sampling.so. Right control is based on output time. Region is only for solid. So this in order to do this Joule heating thing, we need to think about functions. So this is yet another way we can do a customized way of heating, internal heating. So we have to use these functions inside the control dictionary. All right, to initiate that. Decompose parallel dictionary and FV solution. We should know what they are. There's nothing here. And let's take a look at the decompose parallel dictionary. It should be a Scotch method. Okay. Now this is the simplest way to split up your region. Okay, let's take a look at the solid. CD solid. Clear. We have a block mesh dict, which I'm kind of not interested to look at because it's pretty repetitive. Let's take a look at FV options. Okay, we are FV options. So in FV options, we also need to put in the input file for a Joule heating source. All right, so you put heating and then you open and close the curly braces. And if you want to have anisotropic electrical conductivity, we can specify using this highlighted portion. Otherwise, all OpenFoam is going to see is this highlighted portion, which says there's no anisotropic electrical conductivity, which kind of makes things very simple. Okay. Okay. So that's how we implement a electrical heater. So let's take a look at the FV schemes. FV schemes, this is DDT is a steady state, gradient schemes, Gauss linear. Now Laplacian schemes are very important. So we have default is none, Laplacian, alpha and H. That is Gauss linear uncorrected. Laplacian of this Joule heating source, sigma Joule heating source, I think this is the voltage. Gauss linear uncorrected. So it looks like we have to put in lots of entries in control dictionary, in the FV options, FV schemes, and even perhaps the FV solution. Right? Okay, looks like the FV solution doesn't really need much input. All right, it needs this Joule heating source V, probably the voltage. Okay, so we have a simple non-orthogonal correctors. It's and then there's a relaxation factor for H. Okay, which we won't delve too much into. All right, so block mesh, nothing interesting. Okay. So we have taken a look at the system file. Let's take a look at the constant file. So, oopsie. QA, and let's see constant. So we see the region properties, and then we see the solid, the thermophysical properties. Oh, okay, I think I went through that already. Okay, so last thing we want to look at is this 0.original. Oopsie, I keep pressing the wrong buttons. CD, must be getting a little sleepy, but okay, solid. Okay, so we have four things to look for: the boundary conditions. First thing, temperature. On the left side, it's a fixed value of 500, like right side, fixed value of 500. Top and bottom are adiabatic, front and back are empty. So this is a 2D simulation, basically. Same for pressure, front and back's empty. Everywhere else, we all have this calculated. So this means for every, if you see this, it means for every boundary, it's the same thing except for front and back. Okay, so what OpenFoam is going to see, or the C++ float is algorithm is going to see, is going to assign this calculated value to all patches. Okay, all patches. And then for the front and back patch, it's going to reassign that as empty. So what we have is that every patch except the front and back is a uniform value. It's a calculated thing. It's uniform 100,000. And then we have a front and back that's empty. So it's a 2D case. So pressure isn't that interesting. The more interesting thing is the Joule heating source V. All right. So on the left side, it has a fixed value of 1.5. Right side is a fixed value of 0. Maybe it's to do with the voltage. It could be. It could be. So let's take a look at the sigma, which is I think the conductivity. Wonder why there's this slash here. Sigma. Okay. Alright, sigma, there's this internal field which is a uniform conductivity of this value here. Probably, yeah. Probably it's some carbon or something like that. It might be. I'm not sure. But everywhere else it says it's a zero gradient. Okay, so basically we have a uniform field of this much and everywhere else is zero gradient. Means the sigma, or I think the conductivity, is basically constant. And it should be. Alright. All things have been said and done for this case. Let's go do all run. And we put an end there. Okay, we'll see how long it takes. Then take a look at the JouleHeatingSolid.OpenFoam. I have no idea what that is. I wonder where that came in. Okay, must be one of the functions that they're running. Okay. Let's see the log chtMultiRegionSimpleFoam. And remember, when we use a suffix, we can see this solid coming out here. Okay. So adding to radiation model not effective, not active. There's no radiation model. So this is what the output is. So creating finite volume options in system FE options, and then it's a Joule heating source. It says it's a heating, and then it's using some scalar electrical conductivity, which is sigma. It is read from a file. So okay, so we see the thing kind of like heating up and cooling down, the kind of thing. All right, so that's how it works, I guess. There should be a heatsink somewhere. Right? Okay. So basically, these two left and right fields, they are the heatsink for this case. Let's see how long this thing is supposed to be running. A solid control dictionary. Oh, the control dictionary is in the main file. Alright, so this is supposed to run for a simulated time of 20,000 seconds. So in every 50 seconds they write, oopsie, every 50 seconds they write something, and it starts from the start time to the end time. And it's supposed to purge write. Yeah, see, purge write is 2. That means they only keep the last 2 entries of the time step at any one time. So we're about halfway through the simulation. Let's do a touch. JouleHeating.foam. So I'm going to delete this. I'm going to look at. Oopsie. Cancel. No, I can't undo that, but doesn't matter. I want to minimize this, man. Okay. Open. Yeah. Why isn't this thing minimizing? There you go. Okay, anyway, this will do. JouleHeating.foam, and we can always press F5, and we can take a look at the temperature, which is kind of not showing up for some reason. I have some sort of bug. Oh, right. Well, because it's deleting, it's probably deleting stuff as we speak. So see, yeah, now it's skipped ahead of time. So we'll probably have to wait for it to run completely finished before we do anything of that. Do anything required. So I mean, before we can examine the results. Sorry. So yeah, before we can examine the results, we probably have to wait for everything to finish. So I'm going to press F5. We take a look at the latest time. The data is gone by then. Yeah, so every few seconds it changes, so looks like we'll have to wait. I'm gonna fast forward this thing. Alright, it's done pretty quickly, and then we have a graph. I think we can look at the create graphs to see what's going on inside that script. So alright, this looks more complex. Okay, but basically it plots this temperature with some as a function of x, which is fine. And let's see the CD 20,000, and the graph will be inside here, I think. It's a post-processing case. Yeah, you'll be some kind of post-processing where we have some value of temperatures plotted against either position or time. Okay, let's take a look at the solid VIT. Okay, so we see a very strong we see temperatures going up. Okay, so there is some sort of temperature field. The data is there. So I want to take a look and reload this again. So 20,000 play. Yes, so now we have the temperature. Okay, so again we can take a look at this. Right, so now what is this case telling us? Okay, we have two ends that are being held at 500 Kelvin, but there's probably some internal heat generation throughout this whole block looking thing, and heat is being conducted to the outside. So that's what a electrical heater element would probably behave like. Of course, I think you can use the Laplacian foam to do this, I think, because this is basically a heat conduction kind of a case, and there's no fluid actually being involved. So it's a bit of an overkill to use a chtMultiRegion foam for this, but it is what it is. And yeah, maybe the Laplacian foam, what it does is that it does this it does a transient kind of a simulation, but what we are going for here is steady state. So we can skip lots of that step and just obtain the steady state distribution as seen here. So probably that's why they use a chtMultiRegionSimpleFoam. Not for the regions itself, but by virtue that it's a simple foam for how do you say? It's a steady state. It's a steady state solver for the Laplacian, the heat conduction equation. And yeah, I mean, if we are interested, we can take a look at how these Joule heating sources are defined. There's probably some functions we need to acquaint ourselves with, but okay. I think the goal we want to hit for first is to set up our own case of chtMultiRegionSimpleFoam or chtMultiRegionFoam, which is the transient case, and transient case is a lot more interesting than just the steady state case. So probably in the next video, yeah, since we have already gone through some of this, we want to study other tutorial cases. And let's CD foam tutorials. Okay, and we want to look at chtMultiRegionFoam. chtMultiRegionFoam will have 7 cases to look at. One's the external coupled heater, one's called reverse burner, windshield defrost, external solar load, snappy multi-region heater. Now this is very interesting because we have snappy hex mesh being incorporated into chtMultiRegionSimpleFoam foam. So we don't have to use a topo set and block mesh to do everything. If we have some STL files we want to use, we might want to use snappy hex mesh. Now of course we have this multi-region heater here again. And yeah, that's basically probably a transient case, a transient version of what we were dealing with previously. So before we kind of set up our own case, we probably want to take a look at all of these tutorial cases. Then we can try setting up a chtMultiRegionSimpleFoam case ourselves based on STL files or whatever, so that yeah, we can get a feel of how to set up a case. Go through it step by step, slowly, because learning curve for this is pretty steep, since we have multi regions, and we got to set up patches and boundary conditions for each of them. So yeah, that's the plan for the next few videos if everything goes out smoothly. Thanks for watching. Thanks for watching. It's been a pretty good day today of producing so many videos and going through OpenFoam. Thanks for being patient with me, and we'll see you guys again where we can talk more about other features of OpenFoam. Hopefully more than we can do more things as we go on. And yeah, I'll see you guys again. Bye bye.